I'm going to start a little bit of the background on the Pacific Northwest. Yes, that is my grandfather's forest on the left. Was the he bought for a radio station business. Believe it or not because a left forest was not a tree upper, but he's adopted this plan. But the forest was kind of left over, and we kind of adopted it and taking the timber as managers of that forest. But our offices are in downtown Seattle, in the Bullet Foundation, which is the greenest office building in the world, at least when it was built in 2013. And it has a whole hat of solar panels on top. So I'm very proud of being there. But then on the last slide on that picture, it's Heartwood. We do work in the middle of the city. There's no question about where our work is. We are all about making cities more livable and more sustainable, regardless of their strategy, Mass Timber otherwise. We have become, over the last decade, a leader in Mass Timber in the U.S. And I try not to be too shy and modest about that anymore, because it is, there's several firms in the U.S. that are behind FAIA, just to state that was a fact. And that really happened to a lot of the things that you all are talking about. Just do it. Building the house that we'll talk a little bit about in 2011, 12, 13, 14, starting design in 11, building the church, having opportunities, building Heartwood, and then the passion and the ability, craziness to dive into a whole bunch of code changes there that I was tapped on the shoulder by AI International in 2016. I'll talk a little bit more about that. But this parallel between design and research at building prototypes and then checking your work has been all about the mark practice of how people. So that first prototype, right my son there on the right side was the tea house. And I didn't know it at the time, but when we came online in 2015, our families now lived there for 10 years. Our smaller family, since I have 20-somethings and one piece was in Atlanta for the Harris campaign, and it was absolutely thrilling to be back here 6 months ago and be part of that. And then be here as well in a different time, in a different era. But that family home was one of the first structures in the U.S. made out of cross-laminated timber. So we went out on a big limb. I spent my own money, and as I told my group today, it cost us 8% more. It was $65,000 out of the total cost of the house. And those were choices that I made personally for our family as both architect and the owner and the financer of this process. So that process really accelerated my learning about mass timber greatly in so many ways. I can't tell you how doing it with your own hands. Andrew Buddy does, that you all know as a developer, that really sharpens the learning curve very, very quickly. And I'm really proud to say we didn't make any major mistakes and did have a couple of years of research going into it and a lot of partners in that research. But one of the things that was really exciting to me was the prefabrication. And a fellow of us was talking about this earlier, about how technology has changed in architectural firms. I don't use Revit models. I'll show you some of that do. And I've got a whole team of people that do them. They're spectacular at it. But those Revit models have really fit into that prefabrication, as well as prefabrication for many materials, but especially for that picture right there is actually the 850% of sort that we used for our CLT house. They came delivered in little bags. They were all barcoded and numbered. And so the contractor just had shop drawing fast whittles of that panel at that place. And it was pretty phenomenal to see that level of precision and accuracy. And that really, he did get up that mass timber in 2 weeks in the middle of a blustery windstorm and rain. They had the worst blustery part for 2 weeks of December. I think it's had about 10 years. So that was one lesson I learned is don't put the mass timber up in December. But that was pretty obvious. It also taught me about how to measure, and this is really important for this conversation, about how to measure your mass timber. How to measure your carbon, how to define carbon, how to understand it. It brought me into this whole dialogue that Buckhead is even right now in here in Atlanta, and it's really exciting. But mass timber with the shop drawings, you can know the cubic meters, the cubic foot. You can measure that, translate that into 4 feet, which is a lumber term, and you can even translate that back to the trees and back to the acres that they floated. And that whole circular economy motion was really exciting to me because architects will often ask, where do you get your materials? How do you source them? How do you specify them so that they're lower carbon? And here I'm also being asked, well, how do I know that high forests on the help as well? And in the Pacific Northwest, there's a lot of social license that's very heated about whether we should cut trees down or not. And then we lost the lumber industry lost the Northwestern wars in the 1990s, and a lot of mills were shut down. This is a very active discussion that depends on people's families and lives and jobs and the health of all of our forests, since all of us share those values. And so part of my question that's interesting to me was, how can we think about the way we use forests in a little different way so that it can provide both the economy to rural economies, but also encourage the health of the forests? And so the dialogue about how healthy forests are so important and what our role in them has been really interesting part of our this is my husband. I'm taking a picture. I'm looking just like worry up. It's like 30 degrees up on the top of the mountain here where my grandfather's property is. We take this seriously. We are up every month or so on top of Orcas. And we're managing my own grandfather's forest, which was unmanaged. My family crewmen didn't manage that forest for 6 years. And so we bring family and friends up there, and it's one of the most healthy employees things I've done. Essentially, once they have life. Then we had a chance to build the CLT church, which is not really made out of CLT. It's one wall, which is against the fact that it's sanctuary, and it's structurally supported by steel. So I got to learn a lot about hybrid systems really fast. And this was a delightful project. 2 different contractors spoke in these projects. Neither one of them had done anything super structural engineers. We just worked together and made it happen. And in this particular project, the church, there wasn't really necessarily an aligned group. It was that I showed them renderings of what that wall would look like. And they said, oh, good. I think it's great. We like to be part. So it was really the qualities of light and space that we were able to do that. But here I did learn a lot about the steel, the custom steel that was needed for those 17 panels of that sort of structure out with the steel seat panels at the front. And that was interesting to add to the humility. We weren't doing structural books, you see in the space. We were doing what you call the decorative, because it's not. Let's say you need 40-foot high panels, 8 feet wide, or it's just like our hardly think of it, but they're powerful. And they were a key part of the program and work. So right around that time, around 2016, I got tapped on the shoulder by AI National and to go be part of this co-writing committee. So this is what really comes back to policy of how this kind of community, architects, engineers, developers, policymakers, can really impact sustainable policy in positive ways. And I knew that, but I was saying no to the AI because I said there would be a huge time sink. I wasn't being paid for this. I owned my own firm. I had a small business. I have 7 employees editor. I work with all the time. And it was an enormous decision. I said, I can't risk practice. Nevertheless, I did stay in the end after they asked again and again and again. I agreed to go to at least one meeting. When I got back there, it was a little bit like some aspects of this. What Mass Timber? These are people that are on the committee to change the codes. It's not safe. It'll burn up in the fire. All of us saw that excuse me, less, but concrete industry and steel were right there sitting at the table, very balanced, as their voices were heard. They were strongly opposed to many of the things that we were suggesting, and we had to prove it to them. But concrete is still easy. It was a fire guy. We tried sitting about some 6'9" fiery chiefs of Columbus, Ohio, telling you how boys are going to burn up with the fire and the next time it goes up because all of that wood building stop. And you have to figure out how to break down those silos of knowledge and reach out and understand their perspective and how they then create science and research, data-based, data-driven to move to the next level. I did this for 4 years. The key was the 5 fire tests. The 10 fire tests over 2 code cycles, and we developed these fire tests collectively and with the fire protection engineering community on that. That's 6 out of the 18 folks. And we did fire tests after fire. That's one actual, the 5 in the Washington D.C. area in Baltimore at the Bureau of the Firearms. And then in the next code cycle, we did 5 in Sweden research. So Sweden, the outdoor facility that these show here. And what we showed is, I hope you all know, in that it's super safe. If you build a char layer in there, a char layer is the layer that's designed to disappear in a massive fire. And then that fire disappears, And I said, that's like, and then that structural layer behind it is, and you're approved that is kind of and these are, well, we have to screw this stuff. And it convinced the fire community of the code committee that this was indeed safe. Everybody except my 6'9" 5 Gs of Congress voted for these policy changes, 8 stories, 12 stories, and 8 stories. And there's different fire protection for all of these. And these are now codes that one can use, even if you don't adopt the ICC codes in your state when it's still in your jurisdiction. They're available for any code. And any authorities would have jurisdiction, which is another word I use to learn the AHJs to adopt as part of their building code process. So I'm going to talk a little bit about Heartwood now for the rest of this time. This is an 8-story building in Seattle and on Capitol Hill. And we were lucky enough, after finishing this huge amount of work early January in 2019, I ended up writing a grant to the U.S. Forest Service to help implement one of these and to try to bring it to a client. And we brought that grant to a client in August of 2019 after we received it. It was a small grant, but it was about $250,000, which records of a $40 million project cost, $28.5 million construction cost. Is a drop in the bucket to solve them. But it allowed us to do that upfront, incredibly difficult time where you're like doing a couple of different schemes, and you're comparing costs at a conceptual level, and you need not only the architect, you don't need just the urban, it's just totally just design. You need the structural engineer, in our case, the acoustics engineer, and the fire protection engineer, as well as the contractor at scale and the timber factory. So we had this incredibly rich, vertically integrated team that worked together for about end of August to end of October. We got conceptual pricing, got construction in around November from these 2 schemes, and I learned as we were today, but that's similar costs. Do I say we were cheaper? Do I say we were more expensive? I said similar costs. And when you know you're in concept design, good developers, your contractor, you know there's a long road ahead of me. And so having similar costs at a certain point is about if it had come out wildly lopsided on where we think as there's just like the project was 67,000 square feet, 60,500 square feet, 126 units, 113 studios, 13 one-beds. It was for a non-profit owner called Community Roots Housing, which is typically specialized in affordable housing. So that, as you know, is 60% of AMI, the average median income and lower. And this project was being this by an outside consultant who was like direct client as workforce housing. And she was kind of done as an advisory board member because they got a lot of land and they didn't have enough people to begin to execute these projects because of the frenzy that was happening in 2019. So she proposed all year developer fee, and I'll come on and we'll do this project of workforce housing, which means we're going to test the system of light tech funding. We're not going to go for housing. With the light tech, we're going to go 60 to 120% of AMI, which is still quite high in Seattle, as we've got a lot of influx of tech workers that bump up their AMI average median income. And that's a really key thing to consider. So there's you have all the market rate housing that's doing its thing really well. Got this affordable housing over here, you've got this gap. And so the brilliant thing that my client AP heard developed was this model for workforce housing, which had no public funding other than the private funding that the grant and some of the paid affordable housing provider ended up putting in this project cost. But it was conventional loan financed. AP was able to secure a very good interest rate in November of 2021, construction. And that was the majority of the capital stack. But then the rest of the project came from private equity. And I'm being candid about that because this was a really forward, progressive looking project. And to it attract the interest of a number of people in Seattle that they were interested in trying to create a project that had housing solutions in this workforce space that had not been underutilized in Seattle, way underutilized, and also Mass Timber. And those two together that bought both of the capital stack. Just, architecturally, we built on a parking lot. The owner owned this brick building right across the street, Capital Goods Housing. That is a community that was 30% under at AMI, so very high needs population. And our building needed to both work with that space and create some spaces so the two populations join, and also take away their parking, which was not happy for a lot of folks. So we came in with a lot of community meetings, a lot of outreach, a lot of caring, a lot of listening, and develop a space, a courtyard in between that falls apart by the development red line that really tried to bring groups to communities together, the workforce housing communities that voted on, the people that worked out. But they were on the same lot we did at that lot boundary investment. And so our lot ended up being about 13,000 square feet with setbacks. The footprint is 8,500 foot site. And we hope it's for most of people, hope it's a very efficient building. I actually needed to run those numbers. I think I ran them at 80 days, 4 or 5% per floor. But these are small floor plates at 8,500. That's 17 units per floor. And the ground floor, it doesn't have a lot of amenities. The amenities are outdoor courtyards and where its location is. So you all talked about amenities, how important they are in the relationship of the neighborhood. We live in this at the height of Capitol Hill. Everything's walkable. There's no parking required, and really no parking needed in this particular site. Seattle has very good transit and bus systems, and it's extraordinarily walkable. One part I did look at this was walkable. I walked over here from the Kimpton Hotel. It took me 20 minutes. I had to walk home Peachtree Avenue. It's about 10 minutes. It was a little bit too painful. But not too bad. Really, it was coming out the fresh air kind of tried to wake me up a little bit. But walkability is a really key thing, and so that's another aspect of what you all are doing in Buckhead. That you need not is intentionally walkable to something. Yes. So no parking, that was a great thing. And we worked on small units. You can see this is the smallest, small, 321 square feet. It's a studio. We just have laundry down the hall on 2 floors, not on every floor. But it's a simple shaped core with the structure, the steel braced ERBS, which is braced buckling, string, brace frames. I think I got that right. Thank you, structural engineers. And it was a steel system that was also pretty quite the adjusted kind. And there's also another lateral brace it's about to have me down the hall. So we made our hallways small, efficient, and kept our common spaces quite reasonable. This is a picture of a structural system with the lateral bracing in between, and all of the steel is shown that black and white drawing. All the wood is on the right hand side with the brace plate placed up. But you can also see what we did, and I'll show you some pictures later with the deck. So out of that ice frame are these lateral elements that go into the deck, that inset bolted down 3/4 inch steel, and that allows, we're in a seismic region that's very difficult to earthquake area. So that allows the whole building to move and for the diaphragm to participate in the actual structural solution, lowering some costs in other ways. And I'll show you some evidence of that in new construction. These are some renderings that our office did on the left, and then the final on the right. The structural grid, you can talk about, we did not have a single structural grid. We had a 12-foot-2 grid, we had an 18-foot-8 grid, and the reason is because we weren't designing to the optimal structural grid. We were designing, structural engineer. We were designing to the performer. And our performance told us that we needed more units, the rack. And the more units we got, we put the trash underground, we put the electrical transformer underground, and we put everything as possible, as many units as possible. And we designed, we have a very small site, it's a style, and we designed that capability as possible to work with the system. And that was what really made it work. As AP told us that in the first week. This was not, we needed 115, really got it right. Oh, we need 6 more. Okay, we got 121. We'll need 5 more. 126. Okay. And that was the kind of attitude of the part, knowing that there's a difficult Mass Timber. I mentioned this a little bit about the BIM coordination model. This is the individual of our office. It's not a Revit model, but one thing excitement about moving all of these things together in our hands was very extraordinary. I'm able to use that BIM coordination. You could see the holes on the right-hand side there and how those vertical systems did go into place. And all of those holes, all those panels were drawn in place before here. Under construction, what does a tight site do for you? You've got a really tight one here. And we had just-in-time delivery. There was a little swath of a place that a flatbed truck could come up and put that timber on. The timber went up before. It was frankly the easiest thing about the job. The tight site was a challenge. You can see the crane in the background. It's in that courtyard, and we had to have everybody in the brick building when we were taking it down in case there was some kind of a tragic accident. So we had moving 37 floors on clients out of their brick building homes in one weekend. There's not a real fun thing for homes to afford, but it was necessary because of the urban qualities of the site. There's a picture of the construction. You can see the local blast tape, all the bottom, the movers. We do have a wet climate, and everybody knows that. There are slides between panels. That local blast tape, which is extremely waterproof, was up there in about 2 hours after each one of these panels was put down. The tie bit around the columns there is just for protection during construction. That actually all, of course, the glue lamps. And you might notice something else that the beams aren't quite in sync that, and that's because we're trying to be most efficient with the fire. The devising walls will go in units, but we didn't really care that much. This was a design concession I made between how deep the beams were in one unit versus how deep the beams were in another unit, because people aren't going to go back and forth. And so we were able to save some dollars there and save some fiber as well in that piece of process. There's a picture of the core going up. We were using Mass plywood panel stairs because of their strength. We have a stringer that went from floor to floor, and another stringer from floor to floor. And then in the process on the right-hand side, there you could see in the CNC factory, timber laminate in Portland, how that CNC cutter just cuts out those treads. So that's ways and get a fabulous thing to happen because you guys be able to create these art pieces down over our area, which were kind of pedestrian walkway areas with the MPP stairs and the stair treads. And so we have to use that waste again. But those stair treads went up simultaneously with the core, simultaneously with the steel, and simultaneously with the broad rectoid Mass Timber columns, big stair floors. Here's some pictures about how it's all that coming together, and it wasn't easy. This was probably the hardest thing, was getting that steel tab in there underneath the BRBS and attaching it to the top of the slab, while at the same time having moved the next CLT slab go on the next one. So there were some sequencing issues that our team got really learned from, but the coming together of steel and five was done their learning proposition, and we got better at it. The installers got better at it, I'm sure. It was both a detail issue, structural engineer, not to blame the structural engineer at all, but there was just, we hadn't really thought that far down so you're going to get that big slab of those tabs coming out that need the lowery joint. And because there was some oil in the bus of the stewardess could see it, which came off really easily. I think this slide is for John. Is that like me? Yes. Because this is what the style looked like before we poured before we put the acoustical barrier on, because we do have a dry slide on the bottom. So, but then we poured dimension 3/4, a non-combustible topping on top of that. And I just didn't kind of show this stud trap raised off the CLT with speakers for like entertainment of some contractors and other. But we also needed to do concealed spaces on the top because the code's out upsetting. And so it's just a low tech film and some gypsum wallboard and all the software. But it also made sure that as an architect, we kept those recycling part, the skilling plans down as minimal as possible. At the very beginning, the RCPs, we were drawing the 8 weeks to plot the feasibility study because they were this impact because of things like this. So here's the building finished. It was opened. It came online in the 2023. Which is so long ago right now. And it's 90% leased up. It hit a very difficult leasing point scale, where instead of the frothy residential market we had pre-COVID, and then the different frothy thing in COVID, there was that huge buildup of multifamily units. And so we had 15,000 market rate units coming online. The that our project was coming online, which is about twice as many as we probably created in 1 year. So we didn't place up as fast enough as I would have expected, and we all expected, and just being candid here, but it is now 90% leased, and the almost this will be on to its next, so that's a good thing. Some lovely pictures of how it kind of nestles in that with the brick building, closeness of that urban context, connection back to the streets on the right here. Interiors, we were able to keep all of that wood exposed to the extent that we could, except for those sockets that I mentioned that we did gypsum wallboard. In the lobby here in the lab, we did coordinate all of that mechanical, plumbing, etc., very clearly so that it could be kind of kept to one side. And then we were barely able to afford that drop ceiling because just dropped to Western Hemlock. I wanted more of it, and y'all wanted more of it. We ended up painting some pipes back. You can kind of see here a little bit, but not really. 8 of them pipes, one did it of them. But we weren't able to hide most of that. And we had no cooling in this building, which I know is very strange brick liner. So we have to have a fan in there. And you could, as you could see, expose that content, also for cost reasons. But we were able to pop up that wood, they float ceiling, couple more photos. The units are quite basic, quite simple, just to let the wood shine, show up as much as possible. But if possible, we do have blinds, hold blinds, fakely pockets above the windows. And the windows are all simple glazed, and they would hope that we could get afford that. The blind them that we do, so that would be harder. I get similar cost to the standard double glazed. Could be the common spaces. That's an LVT product of the floor, as you can imagine. We left the ceilings exposed. We just kept the mechanical 2 inch vertical shafts. The electrical is running through the walls, and the plumbing is going up in plumbing stacks vertically. So all we really had to deal with was the sprinkler, and that just exposed ceilings there, as well as the beam in the column. So we kept it kind of a looser industrial look. Bike storage is a big deal in Seattle. Bikes are a big deal in Seattle. And those exit stairs made out of that end product was really fun. They're not formal stairs, just 2 sets of exit stairs up, and that's too. It's kind of operationally, I mentioned the triple lace windows. We had to polish was we needed to be a grade 4 level, which is not high. It's still grade 5 is, but it's a fairly strict multifamily standard that's they developed our Master Buildings Association, so it's considered contractor friendly, and it's gotten a lot of uptake. And so the city has begun to use it as if you want an extra floor, which this gets to Buckhead, you need to go build green 4. But we didn't get anything from the Mass Timber other than cooperation with the Jeffers. So, and the extra floor came out of a process that was done 2 years before the project came on, was existed in anybody's mind. And it was certain lots were upset around the city of Seattle. But if you got that extra floor, you had to perform the built green 4, which is not that hard to do, it turned out, but it was something. And the Mass Timber did not get us the edge for that. We would have, it's required a similar to kind of a meat light color in your meat plus, but there was a lot of requires with channel. So the Mass Timber certainly helped, but it was not like a one size fits all. Embodied carbon is not regulated in Seattle. I don't know that it will, but Washington State has been flirting with it for a long time, and it often goes back to we want lower carbon buildings, not Mass Timber buildings. Okay, won't be less far. But how do we report it? And this building had a low UI of 23.9. We were 23% better than our very stringent origin codes in Washington State, which are very rather some would call them aggressive laws. But and a lot of those techniques were, using extra insulation on the roof, which is what here, and it's achieving its insulation. You have to hold it super cold, but sun cold. Very efficient energy, but emergency system, 90%. Very efficient. We did gas in this, not all electric, which is pretty much standard up the West Coast now. But this building slipped in right before that. 97%. It's just gas firing to water heaters. And then a little bit of the envelope, the triple grades, and then they'll help lifestyle extent, which was everything came. Okay, so now we get to the embodied carbon. As I mentioned, you can measure this, and we can all measure this better because you have the air office with architects. So, and it's so we can measure the steel. We can measure the slab on grade slab concrete foundation, and we can measure all the mass timber. So the total was about 1,000 cubic meters of wood relative to, I think it was 250 meters of concrete. So 4 times the amount of wood, but 1 time the amount of concrete. And we did building up out of the ground because we wanted to use less concrete. And we had to do parking, so we were pushed into that. And then steel was quite low. It was, I think it's 15 cubic meters. Of course, steel is heavier, but it's not as much area. So it was about a 1 to 4 to, we'll call it 0.5 ratio.
Okay.
So measuring is the first key. And then we also designed around this idea of low carbon. Design is a powerful tool also. Taking all the steel connectors out of that 2-hour wood joint that was required, that was an amazing thing that we did. It turned out to be rather easy. The hardest part was getting the city officials to rate this as a 2-hour joint, because that was required for 8 stories. And so having to introduce this international tape that was placed in the joint itself, and having to convince the city that the quotes that I have health authority that this solution actually met the solutions was creating policy through research on the slide during a building project. We met several times with the city of Scala. They were really cooperative. They just wanted to know, because they're really dualistic, but these connections anymore. There never are for mass timber. So we're in the process of the industry of creating those, but the lowest are key, and they're gold standard in the US, as you all know. So the other thing we did on the right with the green there is talk about this as a future-proof building. And so how long is this building going to last? That became a big discussion, both with our financiers, the appraisers of the building. Like, they were so excited. It's a wood building. It must be 15, 75 years, maybe 50 years. So we're going to stick to what they're going to be on. So stick, they shrink all the things. Wood. This is not stick. It's not like wood. So this is mass timber. Well, it's mass timber. We don't. So we start comparing it to the quality of a concrete building, and use concrete right on there. This is a quality concrete building. It's the same. It's not type 1 construction, but it's the same quality. And partially to do that, we brought the Seattle Fire Department in to walk through the construction site. And they didn't know what they were going to say. It's like, some studs here and there, like with Frank, this and that. I think going up and they just hung those with them hogs, and just, this is going to burn down. They didn't get to it. This was going to burn down. Once they saw it, they said, this building will last forever. And it probably not true, but it's the way it could last so long. And once they saw, it's not only out this huge tradition of heavy timber buildings down the warehouses down the water that are made out of incredible timber, and been there for 150 years. And we love those buildings, office and ground. The tech companies love those buildings. So this is bringing that technology back to the future, go figure, and showing them that these buildings did last 120 years, and these are laminated, and they don't even read as heavy timber can also do, but because of that class lamination, it's a much stiffer building. And so it was relatively easy to bump that. The appraisal started time up to conservative 100 years, which I really believe is conservative. But then also, we wanted to make sure that we configured this building. So we set the start up to about 18 inches from the slab edge without water edge. The water will live on this facade edge, and they have really cheap fiber cement side. And then we set the columns away from that with the kitchens, of course, to prevent any sort of leakage and damage over decades by the water. I mentioned before these are sustainably harvested from forests that we know well in our region. I'm also bringing this up to remind y'all, you have sustainable forests in your region. You have a steel tea plant in Dothan, Alabama. I looked it up on my phone. It's 192 miles from downtown Atlanta. And I would really encourage you to go visit that manufacturer and just see what they're doing. Timber Lab is the post processor, which we used also. They have a sister company in Portland, Oregon, down there at that. And they take the glulam columns and leaves of the steel teeth panels, and they cut them appropriately to land on that site perfectly, according to the shop drawings Denmark. They've all done. So we had to do an LCA as part of the U.S. Forest Service. So we had put money aside for this. So this is how it was funded. We did bring experts in, and I think the LCA technology has gotten even better since we did our LCA in 2023, using all the software that are out there. One click is kind of take it over the world. FAIA is always very good one, and then Tally as well. But there are some fairly extensible lifecycle analysis software that architects can use, owners can use internally. And I want to make it sound easy, even though we didn't take a necessarily easy route, because we had rivers Washington in our backyard. There are craters of many different ways. And we just felt it was great to be able to advance this brilliant PhD thesis on end of life. So this LCA that I'm about to show you did go through the A1 through A5, which are all about, but it also included the C1 through C4, the end of life work. And that was a big deal for us because, as far as we know, that hadn't really been quantified in many ways. We also then did a comparative LCA, and that was one of the critical requirements by the Carbon Leadership Fund. And they said, it's great to do what you do, but let's do baseline as well. So because it's a grant and this was not inexpensive, we were able to, we had the Heartwood Reddit model, but we were able to model the superstructure for concrete building that was using post-tension slabs, and it was a commercial structural building design. So it was done by our structural engineer who had a vested interest showing how they could produce commercially efficient structural concrete buildings. And so we had 2 models, and then that was the basis for the big slab. So going forward, I'm not going to get into all the details on the left there, but the big picture of the green and the middle of the gray. If you say how much did it cost, but how much LCA, how much carbon did it take to design and build that concrete building? And that was our baseline, that 100% was literally we got out of that model of the GWP global warming potential out of that concrete baseline model that we had modeled separately. That was our baseline. Then we also modeled in parallel the Heartwood building, and we had a difference of 38% for the superstructure of the building. We included the foundations, we included the column beam structure, we included the core. We also included all of the extra fireproofing details, like all that gypsum wallboard that we needed because it had to do that per code that I helped write. And we also, of course, included all the lateral systems, both input systems. And we were as equivalent as possible in that comparison. What we didn't include was the functionally equivalent stuff around the edges. So we didn't include interior design, didn't include the facade, the windows, because in our plants, it's going to be the same for concrete that is right for our Mass Timber Embodied. So superstructure, 38% less carbon than a concrete going at each stories. Now that doesn't count the stored carbon in the work, which is that green bar. So if you count all of the carbon that's inside the material that's being held, then how does that compare? You should also subtract that. So we took that green, and a lot of times this gets confused in the big, like it'll say, oh, wow, we were so, we were like 0%. I do call this a net negative building. I always say it would be stored carbon. Because when you add that green up, which is the amount of carbon that's stored to that wood, in that 1,021.38 cubic meters of wood, you add that green bar, the top of the blue bar, you drop it on down, you can't double count. And you're talking about the number that dotted line down there, minus 3%. So I like to say it's at that negative delta. It's not a lot, right? Negative 3% isn't that much, but it is something. And the most important thing for all of us is to be as clear as possible. So we're trying to do here and be transparent about it and just be open about it. Because, 3%, it's cool, net negative. That's pretty amazing. But 38%, if we can continue to do that again and again and again, new construction, And then the local impression on I put my friend likes that there to also can meet those minus 38%, then maybe we'll get something. Because we all know what happens after the end of life, and being able to reuse the fantastic thing with the C1 to C4 is it forced us to think about what happens to all those panels on the right-hand side. We know what happens to a large concrete building. This was a Seattle project that was around for 24 years, big stadium. It was demolished after 24 years. But we're hoping that these mass timber buildings would have slumber, and when they do come down in 100 years, then they'll be reused. So our end-of-life analysis for our FAIA included the idea that the building itself would last for 100 years. Then we can dismantle all the sport lights, all of the CLT areas, and remove a little bit. Those red stripes, that gets lost. Screw walls and tonnage and cranes and this and that. And so then we can still build a new building. Right? We're assuming in another 100 years. We don't know where the construction is going to be like in 100 years. But let's say we can use pieces in a new building, and it's going to last 100 years. And then after 200 years, our researchers told us we could grind up all that wood and make particle board, and it lasts for 40 years, and we can do it again for 40 years, and we can do it again for 40 years. And so you add up the 100 for the first building, the 100 for the second building, and all the particle board for 120 years, recycles of 40. You get 320 years that building lasts. And then those pieces, they go into landfill, and that cartilage is capped. Some is admitted, sorry, it's not. We lost about 10% in the waste, and we lost about 12% in the CO2, which crashed out. And those numbers were all based on the effects over the last 5 years that came out or WRA. So this was our LCA analysis, our assumptions, and we'll really encourage more and more study on that, and more challenge on that, more transparency. But we were able to also think about how we replicate Heartwood, because that one building is going to make some difference, but multiple buildings is going to make more difference. So we realized in that sort of fun spreadsheet over there that this is a very stupid, simple system. It's function being with CLT floors. And the things on the steel, and we can use that joint and that framing. They'll become stands for the high ceiling between 12 and 18 feet. Residential can happen all day long. So this is really what's interesting to me about this Buckhead conversation is really trying to brand a number of buildings using similar variations of this type. And whether that's student housing for temporary, or whether that's luxury housing for folks, or whether that's affordable housing for your population, it can work in many of these regions, in many of with and without parking. It's a replicable design, and that's really exciting. These are just some studies we've done of the existing grid, impact unit layouts, as well as more regularizing that grid. Yes, you'd love to work in Atlanta and bigger sites, and y'all can get those structural grids exactly tied in, dialed in, so they're perfectly efficient. And we're kind of landing around 146 to 60 a foot 6 in there. And that's but again, it's going to fall with people from in the end. And also going up to 12 stories, the same codes, same detailing, the same challenges in design. There's just a little bit more gypsum way around codes. But it's essentially the same back system as the Heartwood. So 12 stories looks well for hope you want, until you'll get more work. And we're able to do some really exciting studies with some folks around the country to look at what 15 Heartwoods do on site. This is in Sunnyvale, California, on the right-hand side. And these are the equivalent of 15 Heartwoods. Could be it's about a case. So I'm just going to do quickly a couple of slides on another LCA process that we were able to work with the city of New York on. Their economic development also give it the word EPC on a blank site in Harlem. We were invited to be part of the grant program Mass Timber Accelerator, which I think the land base is considering as it are. And this was willing to advance their policy goals, New York City's policy goals, that along the Green Economy Action Plan, so specifically decarbonize durable and construction. And so they had a long and detailed policy memo, and that's to a certain opinion well with this, and so they created a studio where they gave a number of teams $25,000 to that feasibility study. And so we were able to participate with a wonderful owner, Michael Dwyer of Connected York Development, who had a concrete building. He had a concrete building designed for deviate design development, and it was about to go into the next stage of permitting and design development, and he stopped. It was like he knew timber buildings could be done, could be used, and he just felt like he needed to have something that reflected his values. So he, as part of his studio, asked us to replace their concrete slabs with mass timber, and many of the concrete columns names get mass timber, and we did that great. And then we did comparative structural system, LCA, and found it was a 33% reduction between concrete and mass timber for this new scheme. Again, not counting the mass stored garbage, which then bumped it up to plus 14. But it's not a net utility in this case, but it is approximately 86% less carbon-emitted structural system with that concrete building. So with that, I'm going to end the appendix. We're only 1 o'clock. I'm happy to ask questions. Thank you.